Imagine holding your smartphone in the middle of a loud, dark concert. If you asked it to watch the stage, listen to the music, and immediately write website code based on what it saw, could it do that completely offline? Historically, solving a problem like this required sending your personal video and audio feeds to massive server farms. You traded your data privacy and processing speed to borrow someone else's computing power. If you wanted to keep data on your own hardware, you accepted a severe drop in quality, relying on text-only tools that choked on complex logic. Google's Gemma 4 removes that limitation. Released as an open-weight model under an Apache 2.0 license, it natively processes text, images, video, and raw audio simultaneously. The hardware you already own is now capable of frontier-level reasoning. To see exactly how, let's freeze that concert video and look inside the device as it processes the prompt. Older AI vision models crushed pictures into uniform squares, destroying detail. Gemma 4 fixes this with a variable token budget, reading images in their natural aspect ratio. It tracks space using 2D spatial rope, mapping coordinates to calculate exact distances between objects. The audio layer works with similar precision. Sound isn't transcribed by a separate program and fed to the AI as text. Instead, the 2 billion and 4 billion parameter versions of Gemma use a native conformer architecture. They ingest raw acoustic data, the actual sound waves, directly into the neural network. The system observes physical space and acoustics directly, bypassing latency and errors from translation layers. If we scale up from the phone to a desktop workstation, we hit a different physical limit. Processing up to 256,000 tokens of multimodal data simultaneously typically requires industrial, server-grade GPUs. Yet the 26 billion parameter version of Gemma 4 handles this massive context window on standard consumer hardware. It uses an architecture called Mixture of Experts. Instead of forcing the entire 26 billion parameter network to fire for every input, the model activates a strict 4 billion parameter subset. It's like routing a technical question directly to a specialist, rather than calling a company-wide meeting. You achieve the deep logical reasoning of a massive neural network while maintaining the lightning-fast inference speed of a much smaller one. But bringing high-level logic back down to a smartphone introduces strict limits on system RAM and battery life. Standard models fail here because they load all their context into large initial embeddings. They clog the device's memory before the real processing even begins. The small, phone-sized models bypass this using per-layer embeddings. Instead of loading one heavy data block initially, the system injects small signals directly into individual layers exactly when needed, keeping RAM clear and reducing power draw. With the hardware running efficiently, the model triggers a native think token. It plots out its logic step by step internally before generating a single line of output. By combining targeted memory routing with native reasoning, a standard mobile processor operates as an autonomous high-level decision engine. We unpause the video. The phone finishes processing the crowd and the music and immediately outputs flawless HTML code for the website. It executed a complex multimodal reasoning task in real time, keeping every piece of data securely on the device. We are no longer dependent on cloud-based chatbots. You can completely sever the connection and run a fully local, sovereign agent. With Gemma 4's Apache 2.0 licensing and native tool calling capabilities, developers can build secure systems that look at your screen, listen to your microphone, and execute actions on your local computer. The hardware in your pocket has the capacity for complex reasoning. Download the open weights, run them locally, and put your machine to work.